Hello and welcome to the Weekly Space Hangout for Wednesday, May 23rd, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, the EM thruster, China moving towards a moon rover, and another extrasolar asteroid discovered. We've also got our special guest, astronaut Mike Massimino, is going to be joining us later in the show. So let's get to it. Joining me today, we've got Dr. Kimberly Cartier. Dr. Cartier, welcome.
Hey, Fraser. Happy podcast day, everyone.
I used your happy podcast day again. It's now in my brain, and so I was like, happy question show day. But so again, I've got to make sure I
It's a
give you the
thing. I am
props.
so happy that it's a thing right now.
Yeah, and in fact, when you don't show up, the chat says happy podcast day.
Thank you, chat.
Also joining us, we've got Dr. Morgan Renberg. Morgan.
Hey, Fraser. I think this might be the first show that we've maybe ever done that doesn't cover a single US-based story. Go world.
Go world.
That's awesome. All right, so before we get into this week's show, I just want to remind everyone a big thanks to our good friends at the WSH Crew. This is the online community that joins us, surrounds us, gives us strength, and organizes all of our guests. So if you want to sort of take your connection to the Weekly Space Hangout to the next level, if you want a group of people to give you comfort while we're off the air over the entire summer, that's why it was created in the first place, was them to commiserate one another. So you can always join them and chat space news over the summer and be a part of this community. So go to wshcrew.space and they will be glad to have you join them and put you to work organizing guests for our next season. All right, let's get into the big stories. Oh, what do I want? Okay, Morgan, let's do it. Now, Paul's not here, so we're having this conversation in his honor. Let's talk about the EM drive.
This might be the original Kraken. I can't really think back that far, but this might be the original Kraken. And it's a story that we've covered at least twice in the last couple of years about this thing called the EM drive, which was basically a cone of metal that if you put radiation waves, like radio waves, inside of it at just the right frequency, it seemed to create thrust. And it was basically seemed like magic. It was, have electricity, apply thrust, but it kept getting sort of pseudo confirmed again and again in a series of sort of okay experiments in a variety of settings. But every one of them had some sort of indication that there might be something else contributing to this thrust. And there have been other similar propulsion drives proposed that also have that same kind of result. And so finally, a group of German scientists got fed up with this and got a grant to build like a super duper testing facility for all of these things, to apply sort of the most rigorous standards to find out once and for all what's going on. And rather than take an EM drive that someone's already built, they got the specifications and built one to the exacting standards using the best materials and the best construction. And they tested it. So they set it up inside of a chamber that they pumped out to about 1/1000th the atmosphere of the Earth. They shielded the various electrical components. They hand-built the hardware that basically smoothed out the power to make sure that exactly perfect amount of power was being delivered to it. They had temperature sensors capable of telling whether the metal in any part of it was expanding or contracting, and they could adjust the electricity being given to it to change the frequency to match the new size and shape of every piece of the instrument. They basically went through and affected every one of the problems that people had identified. And the end result is they found thrust. There was thrust when they turned it on, and when they basically ran it in reverse, there was thrust in the other direction, just like you would expect. And so initially that seems like a good thing. But then they took the EM drive and they effectively turned it 90 degrees and set it up in an orientation where it shouldn't produce any thrust on their testing apparatus. And they turned it on and they got the same amount of thrust. And they flipped it into reverse, and the thrust reversed in the same direction again. So basically, now you have a drive that produces thrust in any direction at any time, no matter how it's set up.
Well, that doesn't seem right.
That's obviously not great. And so they think that they have identified what the source of the EM drive's thrust is, and it's the Earth's magnetic field. So the one thing that they weren't able to sort of fully shield their instrument against was the Earth's magnetic field, because you need a very special kind of shielding. And they just it's really expensive and difficult to get, and they just didn't have enough of it to cover the whole thing. But that's about the only thing that is invariant against all their different manipulations. And so they've ordered more of that shielding to block out the Earth's magnetic field.
That's really funny. I get all these flashbacks to every time there's been a scientific discovery where there's a time signal every 24 hours or every 365.25 days. And we're like, oh, look at that highly big coincidence. Oh my God. And people just forget to factor out the Earth.
Yeah. It was a great paper. When it came out about 5 days ago or so, I jumped on it immediately, shared it out, and the paper itself was great. And one of the parts that I thought was really great, I mean, they sort of came to that conclusion that the magnetic field was interacting with the wires and causing this torque, this thrust. But they said, but what was great was it was a great experiment, or a great sort of teaching method in building an apparatus that can actually properly test this kind of thrust, this kind of thrust, or this kind of instrument. And so you can imagine in the future, being able to teach the students to go through each possible element of error that's coming from and come up with a mechanism to deal with it. Like, they had a really nice vacuum chamber. As you said, they had all these parts that were shielded. The one part that they admitted they could have done a better job was get their hands on more, was it mu metal, that would help shield from the Earth's magnetic field. But they have a really great apparatus that they can test things like this. And we hadn't seen that level of testing even coming from places like the Eagle Works group at NASA. So very impressive work.
They did test another propulsion system too, called I think it's the Mach effect thruster. And that one produced different but interesting results. When they turned it on, they got thrust in the direction they were expecting to get. When they basically turned it 90 degrees, they didn't get thrust when they weren't expecting to get it. So that seems like a step above the EM drive. But the amount of thrust that they measured was 100 times higher than the sort of theoretical maximum that sort of setup could create. And physics basically never works in that direction. All the time you think you're going to get X, and you end up getting X divided by 1,000. But very rarely do you get X times 100. And I'm not even going to sort of try to describe the theory underpinning this drive, because it's
shaking a mass back and forth with the resonant frequency of the crystals that and
there's like gravity, vibration. It makes the EM drive sound like a logical physics experiment.
Okay, so I'm going to ask this question, which maybe some of our viewers and listeners are thinking: why are they even attempting an EM drive or a Mach effect drive? Like, what is the purpose of this new type of drive? Like, why do we care?
Yeah, it's because we're faced with a really big problem in exploring the universe, right? Which is, it's hard to get anywhere fast. And really, we haven't made a lot of progress in solving that problem. We use ion drives on spacecraft like Dawn. That's been kind of a new modern approach to doing propulsion. And ion drives have improved the efficiency, but they are really, really weak. They haven't improved the power. And so the sort of future that we all want of being able to sort of, board spacecraft and jet out to Jupiter and then fly over to Saturn and then go check out Pluto and then come back to the Earth, and you're gone a year or a week or a month or whatever, seems basically impossibly far away. And so the big space agencies have basically said no idea is too stupid at this point, because we're basically out of good ideas. And so they'll try anything once and see what works, because who knows what physics effect we're not considering. But of course, these things have to actually stand up to the rigors of the proper testing and scientific method. And so far, nothing has risen to that level, which is just making everything a little more depressing to think that maybe we really are stuck with the various options that we know about, as sort of ineffective as they are.
Yeah.
So I guess the moral of this story is the EM drive doesn't yet work, but it doesn't yet not work.
I think it's pretty safe to say it doesn't work.
Yeah, the EM drive is all but dead at this point. If you produce thrust during the sort of null experiment, and you produce the same amount of thrust that you're producing during the actual testing part of the experiment, that's a pretty solid indication that whatever your thrust isn't going to hold up once you actually get out into space.
Well, back to the drawing board then.
Yeah. Well, and the thing is that there are tons of these out there. I mean, these are two of the most popular ones, but there are plenty of people out there who are proposing vehicles, engines that use any combination of crystals, gravity, resonance, and
ether,
right? and so at some point you do have to, I guess, I mean, I think it's fair to give these things a shake, and as they said in their paper, like, to build a proper instrument to be able to test it was great, and they can use this again later on, the next time they get another potential space drive that works with that word salad of things. So I think this is great, and I think the way you described it is exactly right. Now, I mean, ion engines are moving forward quite a bit. There's the X3 Hall thruster that is able to put out newtons of thrust, not just millinewtons of thrust, if you hook it up to a nuclear reactor. So, there are some strategies to try and increase. And then, of course, there's all of the laser-based propulsion ideas as well. So I think we've still got a bunch of ideas that can be tested out. More space infrastructure. That's what we need. We need orbiting laser arrays at various Lagrange points, zapping ships around the solar system.
Yes, please.
Yeah. But and this was, we talked about this in, I don't think we talked about it last week, but just about the CubeSats that are going to Mars, and just how great that is, that you've got so much infrastructure at Mars now that you can send.
The ones with InSight?
Yeah, you can send CubeSats now to do very specific jobs, and they can send data back, and they don't have to communicate directly. They can just communicate to the infrastructure that's already at Mars. So.
Well, and CubeSats are a good example of a technology enabled by new things like ion drives. Most CubeSats in Earth orbit have no propulsion. But if you want propulsion on your CubeSat, then you're not going to fit a lot of rocket fuel inside your shoebox-sized satellite. Yeah. But you can fit enough propellant for something like an ion drive and tremendously extend the useful life of your CubeSat. And that's just something that wouldn't have been nearly as practical a few decades ago.
Yeah. And I mean, I think that's what we're going to see. I hope that instead of us having some kind of magical new drive, we're going to have infrastructure. We're going to have a nice space station that's going to be constantly traveling from the Earth to Mars and back again. And astronauts can just climb on board and make that journey. That we're going to have various communications relays. You can send smaller spacecraft to be able to go to these various places. So with the Mach drive out, with the EM drive out, what do you like now for your exotic propulsion system?
Teleportation.
Fairy dust?
Fairy dust.
TARDIS?
I like the electric sails. We talked about that about 6 months ago, but just using the plasma from the sun as a way to accelerate. So we're not out of ideas yet.
Yeah, solar sails are a good idea for like one-way trips. So they could, I think enable a lot of exploration in the local universe, but they're definitely not that dream of sort of being able to go where you want to, when you want to.
Yeah. Metallic hydrogen.
Yeah, we don't have an answer yet.
Yeah.
But fortunately, we're not trying to get anywhere that seriously yet either.
That's the most depressing silver lining I've ever heard. It's okay. We're not actually trying to explore. We don't have money or infrastructure to explore.
There's nowhere to go. Whatever.
There's nowhere to go. And no
we're
money
all
to send us
alone
there.
in this big sad universe.
So it's okay that we don't have engines to do it.
nothing
Gotta look on the
well
bright
done,
side.
Morgan.
Yeah. Yeah, there you go. All right. Kimberly, let's talk about your story.
Yeah, so China is something that we've talked. China's new space program that's been ramping up in the past decade or so is something that we've talked about before on this show. And just this week is another example of how China is pushing to become one of the leaders in space. Just a few days ago, they launched a rocket that is the first part of their plan to send a lander and a rover to the far side of the moon, which would be the first, if they're successful, the first soft landing we've ever done on the far side of the moon. And it would be a two-piece rover and a lander. And what launched on Monday was part of their communications relay that's going to sit out at the L2 Lagrange point. And sort of the reason for this is because it's the far side of the moon. You can't transmit directly to Earth because it never faces Earth, hence far side. And so what they're going to do is put a satellite out at L2, which will receive signals from the lander and the rover on the far side of the moon, and then bounce those back to Earth from out at the Lagrange point. And so this rocket launched on Monday. It will arrive. It was a perfectly successful launch. They didn't really advertise or televise about it until after it was already over and it was successful. But it was perfectly successful. It'll arrive at the Lagrange point in about 5 to 6 days from now when we're recording. And they plan to also launch the actual lander and rover by the end of the year, which will hopefully get to do some really amazing science on the far side of the moon.
No one's ever landed on the far side of the moon, right?
No,
nothing's ever been there.
I mean, we've had pictures of it,
Mm-hmm.
And we have gravity measurements of it, and we have some idea maybe of what the crust is like, and maybe what the composition is like compared to the near side of the moon, which we've explored in much more detail, relatively speaking. But yeah, there's been no attempt or obviously no success at a soft landing, no crashing on the far side of the moon. So this is an incredible, huge step forward, another giant leap.
Right.
Because I have to make that,
to
make that reference. But the far side of the moon is so different.
Yeah, this is really, I think, an exciting opportunity because we know a tremendous about the near side of the moon, and we know more about a lot of places on Mars than we know about the far side of the moon. And it's somewhat surprising and kind of shocking how different the near side and the far side of the moon actually are. Like we have some reasons we think we know some reasons that might be the case, but there's a lot of questions that are unanswered about why they're so dramatically different.
Yeah, I mean, like if you've seen a picture of the moon, it's about a 98% chance that the picture you're thinking of is the near side of the moon, the side that always faces Earth, that has the light spots, the dark spots. It has some craters, but it's not too cratered. And it's as familiar to us as like the back of our hand. We see it almost every night. The far side of the moon, it looks so different. It's almost completely covered with craters. It's all very light colored, none of those dark maria that we see on the near side of the moon. The crust is a lot thicker. There's a lot more, obviously, been a lot more meteor impacts on the surface. Uh, and just all these differences from what we're familiar with. It's quite literally like there's the divider, the terminus between the near side and the far side, and it's like you're looking at a completely different object. There's no like smooth transition between one side and the other, and we've not really ever explored that part.
Yeah.
If they could bring back a rock, that would be
I wish they could.
Because we don't know how old the far side of the moon. It's clearly old because of how many craters there are. But how does its age compare to the places we've studied on the near side of the moon? We don't have a good answer to that.
So what's the sort of the leading theory on why the far side of the moon looks so different from the near side of the moon?
So there's two pieces to it. Like one, right, is the craters. And that part isn't maybe that surprising because just from the geometry of the situation, rocks flying towards the near side of the moon are likely to get hit the Earth or be deflected by the Earth. Rocks obviously flying at the far side of the moon don't have the Earth as a shield. And as Kimberly mentioned, there's not this evidence of extreme volcanic activity that we have on the near side. That's what makes the Maria that form those dark patches. And of course, lava flows fill up craters. And so in the absence of that, there would be more craters too. So the big question, I think, is why was there so little volcanism on the far side and so much on the near side? And we don't have a good answer to that. But one hypothesis is that it has to do with the tidal forces the Earth exerts on the moon, and that the near side's presence closer to the Earth somehow kept the crust more fluid and the heat, the magma inside warmer, and sort of drove more volcanism on the near side than on the far side. But without any rocks from the far side, we're stuck with just spectral analyses from space. And that's, as we learned on the near side, that's incredibly limited compared to what having just one sample can do for you.
And I think the other part that's really important about this mission is that this just shows again that China is serious about both the robotic exploration of the moon and eventually putting footprints on the ground. I mean, again,
this is as hard as a Mars mission.
Yeah.
It's basically the same parameter problems, no direct communication, no direct line of sight, relatively unexplored territory. This is probably 85 or 90% as challenging as going to Mars, taking out that 6-month flight in the interim. And that's not nothing.
Yeah. And it's a very clever, I mean, I think you really hit the nail on the head there, Morgan, right? It's a very clever way to do something as complicated as a Mars mission, but doing it, at the moon, something that's closer. You can communicate directly. You can learn from your mistakes. It's a very clever way to sort of up your game. And, I've mentioned several times the Chinese logo for their lunar program is has footsteps in the moon. It's the Chinese symbol for the moon, but it has footsteps in it. So, that's the long-term plan, is just, they're testing their space stations. They're building a whole new fleet of rockets. They're going to be building a Long March. Was it the 8? I think is going to be their big heavy lift one. They're building reusable rockets now, as opposed to just dumping them in the mountains nearby, the launch facility, and are moving towards trying to get humans to set foot on the surface of the moon. And that's the new space race. And
this mission isn't
a race if there's only one participant.
Well, no, I mean, SpaceX, when the BFR flies, it can fly to the moon and back just as a thing that it can do. right? When you think about it.
but is it gonna?
Well, who knows?
Is it going to the moon by the end of the
We're gonna
year?
be Well, no, but it can take humans, right? So
And so will China.
so will China
Well,
eventually.
I do want to point out that this Chinese mission isn't just going to be studying the surface either. This orbiter that is going out to L2 is going to make good on something that we've really wanted to do for a long time, which is put a radio telescope on the far side of the moon. This is going to be able to study wavelengths of radio waves that are attenuated by the Earth's atmosphere and swamped by terrestrial signals. And so a lot of people believe that the far side of the moon is the best place in the solar system to study, do radio science, because it has 3,000 kilometers of rock blocking it from all of those radio stations here on Earth. And this is a baby step to finding out, is that a worthwhile thing to invest in?
And they've got, China's got the largest radio telescope in the world, the FAST. They're building the largest steerable telescope in the world. And now they are delivering on that radio astronomy Christmas and putting a radio observatory on the far side of the moon that's completely in the shadow of the Earth's radio spectrum, which is just, that's great. They're mastering it. Of course, if you've read The Three Body Problem, you know why they're doing all this. Spoiler alert. All right. Anything else? Let's move on to my story.
Tell us about asteroids.
Yeah.
Interstellar Asteroids.
So for everyone who I'm sure was paying attention when we talked about it here on the Weekly Space Hangout and literally everywhere, we had this interstellar asteroid pass through the solar system back November of last year. And it was incredibly exciting, and they knew that it was an interstellar asteroid because it was on this hyperbolic orbit. It was coming in, and then it was gone back out into deep space, and so it had to have come outside of the solar system. And then in doing calculations, astronomers realized that probably there's actually tens of thousands of these kinds of asteroids inside our solar system at any one time, that this kind of debris passing from star system to star system is happening all the time. So, but one of the other cooler ideas is to think, well, could one of these interstellar asteroids actually get captured? So astronomers have found, and I'm just going to bring up Phil Plate's article on this. Astronomers have found an object, and they actually found it a couple of years ago. So the object is called 2015 BZ509. And so astronomers did know about this thing, but now a team of astronomers from Spain and England have come out and said, actually, it looks like this asteroid had to have come from another star system. And so their explanation is the asteroid goes in this what's known as a retrograde orbit. So it's orbiting backwards from the rest of the planets, objects, everything in the solar system. It's going backwards out around the orbit of Jupiter. And it has this strange resonance with Jupiter where essentially the two keep each other in lockstep, or I guess Jupiter keeps the asteroid in lockstep. It influences it very slightly, but and it's in a relatively stable orbit. It's probably been in this orbit for billions and billions of years. So I think my wife just caught a bug or something. A fly. All right. So it's been able to be stable in the orbit around Jupiter. And so according to the orbital characteristics, the astronomers have proposed that this is actually an interstellar asteroid. The fly just went past me.
That's really cool. And you said it's around the orbit of Jupiter? Like about that distance?
Yeah.
Is there any chance of us observing it with a telescope or a spectrograph?
Well, I mean, it was already turned up by
It was found by
Pan-STARRS. So that was the same people that found Oumuamua and many of the asteroids that are discovered. The challenge, of course, is that if you want to, I mean, you could do a flyby of this asteroid, right? That's relatively straightforward. Get out to that orbit, do a flyby, take a picture, use your EM drive to get out there quickly, right? Do your flyby. But to actually do a sample return, do something where you can actually find out, like OSIRIS-REx, you would have to cancel out the Earth's motion around the sun, the 30 kilometers per second, and then match up with its orbit. So you would need a lot of gravitational assists to try and actually put yourself into an orbit that would be the same as it. So,
but I mean, we could do it.
Yeah, I don't.
We landed
know.
on a comet.
Yeah, that wasn't going in a retrograde orbit.
Well, fine.
Right, that's the problem. Is the orbital mechanics
All right,
of it
so
brutal.
With the huge caveat that I have not read this paper, I'm going to come out against this and say that I am incredibly skeptical.
You are
of
totally being a
their
kraken right now.
Yeah, of their methodology here. Again, having not even cracked the paper, the way in which they investigated this was to measure very precisely the orbit of the asteroid today, and then to basically simulate backwards in time its orbit to show that 4.5 billion years ago it was still doing a retrograde orbit. And those kinds of what we call orbital integrations are incredibly challenging to do over long periods of time. You might have even heard that we can't really predict the orbit of the Earth beyond a few 100 million years with any real certainty. And to run back 4.5 billion years and make a claim as definitive as this had to have come from another solar system strikes me as an awfully big leap. And even if you can integrate it back to 4 billion years ago, we can't possibly know what else was going on in the solar system at the time. We think Jupiter might have been moving. There may well have been other planets in the solar system that certainly would play on the gravity of this object. Any number of encounters or gravitational interactions could put this single object out of millions that we've studied or observed onto some sort of weird orbit. And so as cool as it would be, and as awesome as I want it to be, I think we ought to be careful about making such a strong statement that this definitely came from another star system.
Well, what would be the orbital mechanics involved for our star system to actually capture an object like that? What must it have done to end up in orbit around the sun?
So that part's not so hard, right? Because go back to the birth of the sun, and we were probably embedded in a cluster of other forming stars that looked maybe something like Orion's nebula looks today, a dense star-forming region with a bunch of baby stars being born, with a lot of objects at their periphery very tenuously held. And as those stars sort of interacted, it's possible that quite a lot of material was actually being exchanged sort of between our star and other stars, between our star and our birth nebula. It's not at all implausible to me that this is a captured object. What I wonder is how we can know that this one is a captured object, not that we've captured objects, which we surely have.
Right. And then the flip side, what are the orbital mechanics that could put a object that had formed in the solar system into a perfect retrograde orbit like that?
Well, we know that this happened, right? Because of Triton. So Triton is the 6th largest moon in the solar system, and it orbits retrograde around Neptune. Now that's a much, much smaller version of retrograde than going retrograde about the sun. Energetically, that's a much larger hill to climb. But we know that there are mechanics and we have plenty of small asteroids or small satellites of all the outer planets that orbit in retrograde orbits around planets. Again, that's a much smaller gravitational hill to climb, but we know that there are physical processes operating at large scales that can put objects into broadly retrograde orbits.
Well, I guess we have to go and visit it. So, like I said, fire up the EM drive. So Arjun is asking,
look the same as all the others.
Could we see what elements are on that asteroid from here? what would it take for us to be able to know whether it is just from the solar system or something maybe interstellar in origin?
Well, we study asteroids all the time for their compositions from here on Earth. And basically the way that works is we watch sunlight bounce off the surface of an asteroid, and then we measure its spectrum coming back to Earth. We subtract off the spectrum of the sun, and we assume that whatever's left is the spectrum of what's on the surface. And we have developed a pretty complicated classification system. Fraser's badly distracted by this fly.
This big fly is just going right past me. You missed one,
we have
Carla.
a classification system for the various things that we see. To my knowledge, and I'm not an asteroid person, a lot of that work has happened in the asteroid belt, which is a lot closer than the Trojan asteroids around Jupiter, and primarily with asteroids that are larger than this one, which I think was like 3 kilometers. So that's a real small point. But in principle, it's totally doable. Whether on that bulk scale, it would look different than a normal solar system asteroid is a different question. Because, we still expect it to be made of rock. And rock is still made of basically the same things everywhere because there's only so many ways to make a rock. Could we tell that it's fundamentally different? Probably not.
Yeah. And so could you do it from a flyby?
I doubt it. I think you probably need a sample because
Yeah.
what you're going to want to look for are fundamental ratios
Right.
of elements like uranium and lead. We know that our solar system was seeded with a certain ratio of, say, different uranium isotopes. And we think that that's characteristic of our solar system and thus would be different. But it might be more accurate to say that that ratio is characteristic of our birth cluster. We don't know how finely tuned that is across some local area of space. So it could be that other stars that formed right next to the sun also have similar uranium isotopic ratios. And even that wouldn't necessarily be, if you found a difference, then that's a cut and dry.
Yeah.
But if you didn't find a difference, that doesn't guarantee you that it comes from our solar system.
But the even more mind-bending thing, you can imagine down, sometime in the future when we've seen many more of these things, gathered samples from many of them and started to see patterns. We're like, oh, all of these interstellar asteroids came from this one star and its planetary disk, and then all those asteroids came from this other one. Like at a certain point, as we capture and find out more of them, we could eventually start to fingerprint more and more of the objects that formed with us in the original larger nebula, which I think would be just,
That'd be amazing.
Yeah. So that's why we want the EM drive, right? All right. Perfect. Well, now it's time for our guest. All right. Thanks, Mike Massimino. That was awesome. And now let's move on to what we're working on. Morgan, what have you got going on?
Yeah, I've got a new episode up on SciShow Space that was, I have to admit, a tremendous amount of fun to write. It's all about the different moon illusions that make the moon seem bigger or smaller relative to other things. And I'll say that in the midst of writing this, and this got edited out of my script by the end, I actually went up to the roof of my apartment building and was up there in the parking lot holding my finger out at the moon, actually trying to prove to myself that the tip of your finger could cover the moon. Mm-hmm. Because even though I knew that rationally, I just basically couldn't believe that it was true. And that tells you how strong the moon illusion is. So I had a lot of fun with that.
Yeah, hold your arm out at arm's length. Hold your pinky nail, no matter sort of how big a person you are, your pinky nail will perfectly cover the moon. And you can do that when the moon is down on the horizon. Or the sun, yeah. And
that's the even crazier part.
And then do it again when the moon is high up in the sky, and it'll block it in exactly the same way both times. And
I'll give you another hint that got edited out of my script, which is I work at a place with a planetarium. And one of the sort of dirty secrets of planetaria is that oftentimes when you go into the planetarium and we have the moon up in the sky, we make it artificially bigger. Because and the same thing's true for the sun, because if you show the sun and the moon on the planetarium dome at their proper size, people think they're totally fake because they just look so small when they're abstracted up there on the dome, devoid of all of the various illusions that we always basically see the moon and the sun relative to.
Yeah, I love it. Oh, that sounds great. Kimberly?
Oh, so I've had a quite busy week at work.
Not to mention getting a house.
Not to mention the fact that I purchased and moved into a house in the past week and a half. So there's that. But I've been studying how the geochemistry of ancient gold treasures can pinpoint its origin. I've been looking at really amazing artwork made from conference research talks, which is probably the best way I've ever found to make conference research talks interesting. And I've been learning all about some new science about last year's total solar eclipse that happened over America. There's still amazing science that's coming out of that. So that's what I've been working on.
Did you get to write about this ice core led Roman Empire story? That is the coolest thing I've read in a long time.
No, amazing. I didn't. That was so interesting. Unfortunately, I did not have time this week to cover that. But go check it out. Go read.
How about you, Fraser?
Well, so I've got something coming up, which is going to be a lot of fun. Which is I've been adding additional guests over on my personal channel on YouTube. I just had a new video come out with Dr. Paul Sutter and myself talking about cosmological horizons. I know he's not here, but yet he's on my channel. He's traveling right now. He'll be back. And so Paul was going to join me on Monday, but then he fell through. But now I've got Eric Berger, who's going to be joining me on Monday, and he actually. Many of the stories, especially many of the spaceflight stories that we share,
80% of the stories we talk about are Eric's stories.
So he is the science writer at Ars Technica and one of the greatest. I'm jealous of his ability as a science journalist and the scoops that he gets in the field. So he's going to be hanging out with me on Monday, and we're going to talk about how he does it, so I can pick his brain. And answer your questions about all the cool stuff that's happening. So check that out on Monday over on my personal YouTube channel. All right. Well, hey, as always, thanks everyone for joining us for the Weekly Space Hangout. Thanks for a special guest. Thanks to my co-hosts. It's awesome. I really appreciate everyone joining us, watching it live, as well as all of you who listen to it as a podcast after the fact. If you do take a second, give us a rating on whatever podcast software you like to listen to. That would be awesome. And of course, a big thanks to the good folks at the Weekly Space Hangout crew. Thanks for taking the journey with us. All right. We'll see you all. Let me move this there. There we go. And this. All right. We'll see you all next week. Now, everybody stick around. Morgan and Kimberly, you get to flee, should you wish. But I'm going to do the Mike Massimino interview now. I know that was very confusing. You're all wondering what happened. So we're going to do that interview now.
Bye.
Bye.
See you guys later. All right, let me just get this all set up. Full screen. Apologies in advance. All right. The special guest was the fly. Yeah, exactly. All right. Is that going to work? Okay, I'm going to remove some things here. Hold on. Apology in advance. Guess I'll go with this. I know this isn't perfectly optimal. All right, let's get started. Here we go. 16 minutes. It's Mike Massimino, astronaut, intrepid science advisor, author, documentary host. Mike, welcome back to the Weekly Space Hangout.
Thank you for having me.
So last we talked, you've since written a book.
Okay. Yes, I have. Here it is. You want to see it?
Yeah.
It just happens to be right here.
Yeah, that's awesome. That's awesome. Tell me how the background. How did you go to write a book?
Well, I like telling the story of space travel, and I enjoy doing that. And I think that a book is a way to get a lot of it down on paper, and that was the idea, was to try to write something that would be it's a memoir, but talk about my experiences, my path to being an astronaut, and then things that I learned and saw and experienced as an astronaut. And it became more of I thought it was going to be like a funny book at first, like funny stuff that happened to me at NASA, because those are usually the stories I told to people, and they seemed to like. But my funny stories didn't necessarily make it in the book. They don't necessarily, something you tell an audience or a friend or whatever that's a funny story. It requires somewhat of a two-way communication technique, I guess, and you can read the audience and see how it's working. You improvise. You can't do that when you write it. You write it and that's it, And so some of those stories didn't work as well as I thought they might. And what the book. So there is some funny stuff. Some of this funny stuff did make it in there, but it's also, I think, a very inspirational story, as it turns out. And that's a lot of what the comments are about not giving up on your dreams and about public service and so on.
Yeah, and I think that's the part that I've really heard a lot about, is just that, you had this real fascination for becoming an astronaut, and were able to pull all the pieces together and qualify and be able to make it. So can you talk just a bit, and almost like inspirational for other people who want to go down this journey as well?
Yeah, for me, it was not something that I thought I could ever really do. I dreamt about being an astronaut when I was 6 years old, when I saw Neil Armstrong walk on the moon on my black and white TV set at my house in Long Island, and wanted to be an astronaut as a little boy. And then as I got older, I just thought, that's impossible. Who gets to do that stuff? And it can't happen. And as I never really thought about it, even, like we had a question about what degree you could take for it to become. I wasn't thinking about any of that stuff when I was going to college. I just wanted to get an education and get a job when I got out, and wasn't thinking about the space program, or certainly not thinking about being an astronaut. And then after in my senior year, I saw this movie, The Right Stuff. I saw The Right Stuff, and that ended up inspiring me again, and kind of a second inspiration when I was in my early 20s. And then after that, I read the book, and I started the Right Stuff, and I started thinking about more what I maybe I could do in the space program. I had an engineering degree, and decided that after working for a couple of years after college, I was going to give it a shot. So I went to grad school and started applying to be an astronaut. Got rejected 3 times. Last time I got rejected, I was medically disqualified too. That was disheartening. I talked about that experience, but I was able to get that overturned. There was a problem with my vision, and I was able to figure out a way to see better, believe it or not. They didn't accept LASIK or any of that stuff. I went through some vision training, was able to improve my eyesight so I could become qualified again, and they can consider me a 4th time. And then that 4th time I got picked. So I think that's, sometimes there are things you want to do, and they're important to you, and they're kind of hidden in your heart, in your soul, and you feel embarrassed maybe talking about them. That's the way I was about it. And you think maybe it's never going to happen. And it might not, but it certainly isn't going to happen unless you give it a shot. And that, I think, makes all the difference. I think just trying is really what's important.
Now, we're having you join us as part of this documentary, One Strange Rock. I've had a chance to preview a bunch of them. I fast forwarded to your episode. I got a bunch of advanced copies, which was great, and I really enjoyed.
Cool. I haven't seen. I guess I saw an advanced copy of that. Yeah. Anyway, good.
Well, you get a chance to kind of walk around. I fast forwarded to your episode. I got a bunch of advanced copies, which was great, and I really enjoyed.
Cool. I haven't seen. I guess I saw an advanced copy of that. Yeah, anyway, good.
Well, you get a chance to kind of walk around through the New York Central Station and sort of look for fossils in the
Yes.
in the walls, and I thought
Right.
that was great, and sort of a
Very
bunch of other.
interesting.
Yeah, I
Good.
didn't
Glad you liked
realize
it. Good.
that stuff was there.
Yeah.
But I mean, I think the whole perspective of this documentary is to sort of get that perspective of the Earth from the people who have been able to hold the whole thing in their eyeballs at one time. And I think, what is that message that we, the folks of us living here on the ground, should take away from what you folks saw and were able to bring back?
That the Earth, in my opinion, the Earth is a paradise, and we're very lucky to be here, and we should appreciate every second we get to live here, because it is so beautiful, and there are beautiful things you can see while walking around the planet, certainly, but when you see it from a distance, I think the Earth was meant to be seen from above. From space, and you can see how beautiful it really is, and just how how lucky we are. I think that would be the one thing I'd want people to understand is it's an amazing planet, it's a beautiful planet, and we're very lucky to be here.
It's interesting. People always want to ask me, if trips to Mars were possible, would you go? And for me, like, I'm not done exploring Earth. It's such a great planet. I've never been to Asia. I've never been to Australia. I haven't seen Antarctica. I haven't been to all these places. So, and I think Mars is an adventure, but there's so many places here on Earth, and I think we don't want to discard what we've got here. But speaking of that idea of sort of, people are planning to move to Mars. They want to colonize Mars. They want missions to Mars. My take on that is always that, we may have the rocketry parts figured out, but the engineering challenges, all the little details are the sort of the to-do list is incredibly long, and I don't think we've really worked our way through a fraction of that. So from you as an engineer's perspective, I would love to know your thoughts on where we really are along that path of being able to try and move to and live on, or at least explore some of these other worlds out there.
I think it's still a ways off to go to Mars. Mars is not an easy place for us to get to. And you mentioned we have the rocketry figured out. Well, we kind of do, but it still takes a long time to get to Mars with what we know now. So unless we have some huge revelation, which I think eventually we will, in being able to travel.
We can get half the robots there alive.
Right. You get what?
Half the robots there alive. Yeah.
Well, you could probably get people there too, but it's just that it takes a long time to get there, and but I do think we'll eventually get there, but I think we should be, and I think we will end up going to the moon first and settling there. It's been a long time since we've had people on the moon, and those were just short visits. I think that would give us the opportunity to learn how to live on a different planetary surface, and I think it'll get us, in the long run, it'll get us to Mars more quickly than if we just try to go there straight off, I think. So I think Mars is still a ways off. I think that it'll happen eventually, but there's a lot to that. I agree with you. There's a lot going on there besides just shooting a rocket ship off there. You've got to be confident that you can live there and keep people alive. You could be, you go there and you can't go there just for a little visit, but because you need to stay there for a while so you can come back at the right time. So it's, I think it's a little bit beyond what we're able to do right now, but eventually, sure, I think we'll be there.
Yeah, I mean, I read Scott Kelly's memoir as he was talking about being up on the station for a year, and just his battles with the carbon dioxide scrubbers.
Yeah.
Right? Like that alone is, you get that wrong, and in a very short period of time, you asphyxiate and die. And that's just one machine that you're depending on.
He probably wasn't feeling it. I mean, we could hopefully do better with a better filter and of alleviating some of that problem. So, but that's right. I mean, it's just, you have to recreate everything, and that's just one of the issues. Is what are you going to do with your revitalizing your atmosphere. You have to take the CO2 out of it, and you have to take contaminants. Other contaminants might be there, and other things that, that's just one thing. You have to be able, because you're not on, we don't worry about it as much on planet Earth because we're on this planet with this atmosphere that takes care of all that. But you have to recreate all of your life support when you're in space. You have to recreate, you have to somehow come up with a plan for water and food and what to do with human waste. And then there's things that might be a little more subtle, like the carbon dioxide, radiation protection. There's a lot of issues, but radiation protection is a major problem. You're going to be exposed to cosmic rays on the way out there and on the way back and on the surface as well. So we can't radiate people beyond what's an acceptable dosage, and we're going to have to do something to protect them. So there are a lot of things. You said about sending robots there. There are a lot of things to consider sending people that you're not going to have to worry about when you're sending a machine there. So it's not easy.
Now, you were one of the folks who fixed the Hubble Space Telescope, and so you have sort of practical experience in going to space, spacewalking, and repairing a machine. And that actually feels to me like one almost undervalued thought in sort of the way some of the current missions are going. Like when you think about James Webb, it is going to be going into an orbit that can't be reached by astronauts under the current capability, but they did put a docking ring on it. So I find that kind of fascinating. And that feels to me like one really useful way that astronauts can learn to live and work in space is to perform some of these functions, to learn the hard way. What are the I know you had to sort of fix a rail on the Hubble Space Telescope, and no one had ever anticipated that, and that's just the kind of thing that you wouldn't expect when you're in space. So I would love to know your thought as a person who has actually been there and repaired spacecraft in orbit. Do you think that has more of a role to play down the road?
I'm sorry, that was the last part of it?
Oh, do you think we should see more of that? We should push more of that. We should try, not just because that satellite needs to be repaired, but because there is value in learning how to repair.
Yeah, I mean, sure, that would be great. I think with the case of the James Webb, they're counting on it working, on everything deploying and nothing bad happening, so that you don't need an astronaut to go up there and do something to fix it or refurbish it, upgrade it, or that we're able to do with the Hubble. So it's kind of it's a different situation. I think part of that is when you build a spacecraft that you want it to be serviced like the Hubble was, you're talking about a lot more money to do that. You're gonna have to make it so the parts come in and out easily during a spacewalk. You're gonna have to label everything. You're gonna have to have the right connectors. You're gonna have to. It needs to be able to be taken apart and put back together again, and that requires a lot more money to do that. And where the observing for James Webb takes place, and that's a better place to do it than closer to the Earth. It's out of our reach from what we currently have to get there, to send people there. So hopefully it'll all work. But we learn a lot from servicing the Hubble, and we're still doing spacewalks and working on the space station, and whatever that next step is, if we go to the moon or Mars or wherever we end up going, we're going to be still working on things and fixing things in space, and it's different than when you do it on the ground on Earth. So I think we're going to, of course, I think we'll do more of that. As long as you put something in space and there's a person around, something certainly will break, and you're going to need to figure out a way to fix it. But something like the James Webb hopefully will be okay on its own.
Yeah, I mean, obviously, we hope that the spacecraft will be okay, but it feels to me like, if there is a problem with, say, the deployment of its solar shield or something like that, just one little kink in the origami, that there's real value to having astronauts who could potentially, it's an interesting trajectory. It's an interesting challenge. It's the kind of thing that wasn't predicted and planned. But when you look at the $10 billion launch development cost, maybe when the final budget comes in, to send a crew up there to try and take a crack at making it work again. That feels like a next level challenge, and the kinds of challenges that we may face in space. So I and I get this question all the time from my viewers, which is like they look back fondly as an immense accomplishment from humanity, not just in launching the Hubble Space Telescope, but in recognizing its importance and going back and fixing it and keeping it going despite the issues. So I think that was a real accomplishment, and thanks for being a part in it.
No, my pleasure. I'm glad it's still working.
No kidding. All right, Mike, we got to let you go, but thank you so much for joining us. Just a reminder, you're on One Strange Rock, which people can watch on National Geographic. You've got a new book. One more time, let's see the book. And I think you're also...
there it is, Spaceman.
Right on.
Yeah.
We'll put a link in the show notes so people can buy a copy. Thanks a lot, Mike.
Thanks.
Take care.
Thank you. All right.